Hello everyone, and welcome back to Thermodynamics Shorts, where I'm trying to distill the main information from the large lectures we're doing down to 5 to 10 minutes. And the lecture that we did today was lecture 5, where we explored the first law of thermodynamics for closed systems using the elapsed time format. So this is what that first law looks like. We know that the change in total energy of the system is equal to the heat entering the system minus the work leaving the system. So I can express that mathematically, but I can also show it pictorially down here that as I move from state 1 to state 2 through time, the energy in my system changes. That change in energy is due to some heat and some work, and I can use the first law to find out how much heat and how much work went into this process. So it's important to remember that when we're doing this version of the first law, and I'm going to try to keep this consistent through the whole class, even though that's not exactly what happens in the textbook, that heat in will be positive. So if heat's entering our system, it's positive, and if it's leaving our system, it's negative, and work in is negative. So if we're compressing a mass, then what's happening is we're adding work to the system. But if a mass is expanding, then what we have is work being positive. So how do we use this equation in thermodynamics? So last class we talked about finding the work. So work is the integral of PdV. Sometimes it's helpful to draw a PV diagram because then the work is just the area under the curve. I find that type of formulation is really beneficial when you have a constant pressure. So this area is just a rectangle. Or if you have a linear relationship between pressure and volume. In that case, the area is a rectangle plus a triangle. Now, oftentimes in thermodynamics, we'll have a process that we call polytropic, where pressure times volume, denoted here as big V with a line through it, to some exponent n is equal to some constant. So that means that we need a value for n. And there are different values of n depending on what's going on in this process. Usually, if you have a polytropic process in a problem in this class, the value of n will be given to you in the problem. So that helps us take care of work and how we find work, but how do we find delta E? What's going on the left-hand side of our equation? First, we remember that the change in the energy is the change in all the different kinds of energies, which include kinetic energy, potential energy, spring energy. So that's like, remember the archer pulling back on the string? What that archer is doing is storing spring energy in the limbs of the bow. But then in thermodynamics, there's this new kind of energy, which will dominate most of our problems. That's this change in internal energy, or delta U. That's U2 minus U1. And remember, that's all going to be equal to heat in minus work out. So in a lot of thermodynamics problems, we'll make the assumptions that this change in kinetic energy, the change in potential energy, and the change in the spring energy are all very small compared to this delta U term, the change in the internal energy. And that's what I mean when I say that delta U dominates most of these problems. Now, this doesn't mean that delta KE or delta PE or delta SE are equal to 0 in actuality. We just think that they're so much smaller than delta U that they kind of might as well be equal to 0. Right? This is kind of the concept of 1 divided by infinity. It's not so much that 1 is equal to 0 in that case. It's just it's so much smaller than the really big number that we're sort of representing by infinity in that case that it might as well be 0. So the same thing is happening here. We're assuming, as what people often call a first approximation, that's a first guess, kind of a crude model, that the change in kinetic energy, the change in potential energy, and the change in the spring energy are all much smaller than the change in the internal energy, right? And whether or not that model is too crude is sort of up to the judgment of the engineer. So you need to know what your application is and whether or not the assumptions that you're making are valid. And that's why I think it's always important to start with the fundamental equation and track the assumptions that you're making. So if we can make all of these assumptions, then delta U gets replaced or gets added to the left-hand side of our equation, and that's equal to Q minus W. So normally in thermodynamics, what happens is when we're using this version of the first law, we'll find the work as the integral of PdV. To do that, we need to know pressure as a function of volume. Then we'll find delta U, which, remember, the change in the internal energy is equal to mass times the change in the specific internal energy. And next class, we're really going to get into how we fix states, how we find those internal energies. But for now, we'll just leave this as the equation. And normally, the process that we'll do is we'll find work, we'll find change in specific internal energy, so we can find change in internal energy, and we'll use the first law to find heat transfer. And that's kind of where we are in our education, but once you take our heat transfer course, then you might be able to find heat transfer in a different way. But in this class, if heat transfer is not given to you, you're sort of stuck finding heat transfer from the first law. So then we did an example. I won't read this example to you, but you can certainly read it if you like. You can practice this problem at home. You can check out the solutions that are online in my notes or in the video lecture. Although I do think that I made a typo in the volumes at one point in the problem, and I forgot this 0 after the decimal place. So I multiplied the volumes by a factor of 10. So check the math, but the process there is correct. So in this problem, this is a first law problem. So we're going to generally use this process, although in this problem, we're trying to find delta U. So we're told the heat transfer. So our order of finding these terms is a little bit different here. But first we find the integral of PdV to find work. We sort of talked about this generic solution that we can get for the work provided that n is not equal to 1 and it's a polytropic process. So we found that equation, and then we used math, put some stuff into a calculator, and found the work. Next, we looked at the heat transfer, which is actually given in this problem. But notice that this problem, it says the heat transfer from the gas is 2.2 kilojoules. They don't specify the sign. They're only giving us the magnitude. So here we have to realize that this from the gas means heat is coming out of our system, which is the gas. That means that the heat transfer is negative. And then we put these things into our first law. Notice that this will become negative 2.2 kilojoules plus 7.65 kilojoules because you're having negative minus 7.65 kilojoules, which turns into plus W. And then we use that to find the change in the internal energy. U2 minus U1 is 5.45 kilojoules. But the problem asked us for the change in the specific internal energy. So I have to divide delta big U by mass to find delta little u. And here we found that that was 29.8 kilojoules per kilogram. So that's all for this edition of Thermo Shorts. I'll see you next time.